Welcome back, physics fans, for our last lesson of acceleration, at least when it comes to the using the formulas and learning our little bits of gravity in this part. So this is the kinematics of falling. Okay, let's just minimize this. Oh, do I have to close it? I think I have to close it and then bring it back up. The scroll bar wasn't working. There we go. So acceleration, this is the definition we've had before. Acceleration is defined at the rate at which velocity changes, which just comes up to the formula. That's the definition. Acceleration is the change in velocity over time. Okay. What makes kinematics more exciting is when the direction of acceleration is in the opposite of the initial direction of velocity. Example, throwing something straight up. One of the most common examples of constant acceleration is an object free falling near the Earth's surface. Mathematically, it doesn't matter which direction you set to be positive, is positive up or is positive down. When using kinematic equations, you end up with the same value, the vector value at the end for all your answers. On Earth, this acceleration is often referred to as the acceleration due to gravity. Acceleration due to gravity. So you'll hear that phrase many times, and we give that a little symbol g. But that's just acceleration, right? It is acceleration, so we can write A is equal to g. The acceleration is caused by gravity, or we could just write it as g. This value has small fluctuations around the Earth. It goes down to about 9.78, and it goes up to about 9.83, and it depends on how close you are to the center of the Earth. If you're on the tallest mountain, or if you're close to sea level, it changes. And if you're near the equator or near the North Pole, it changes because the distance from the center of the Earth changes as we go from equator to pole. But it's averaged out in our Physics 11 class to be 9.8 meters per second squared downwards. So this cannot be emphasized enough. We're going to use this. There's some classes that will use 9.81 because if you average it to 3 sig figs, it's 9.81, but I'm just going to use 9.8. So if you watch other physicists online, they might use 3 sig figs with 1 there. I will still use 3 sig figs, but I'm going to put a 0 here. Okay, and the direction of it is downwards, and how do we define downwards? It's towards the center of the Earth. Okay, so if I drop something, the initial speed is 0. The acceleration for the entire drop is 9.8, and it's always downwards. And as time progresses, what happens? After 1 second, it accelerates to 9.8. And then we add another 9.8. And then we add another 9.8. So it's going faster and faster and faster and faster. So after 5 seconds, it's going 49. After 10 seconds, it's going 98. To get the velocity there is just going to be, since VI is 0, VF is going to be just 9.8 times time. Because the formula is VF equals VI plus AT. This is 0 because we're dropping it. Initially, it's at rest. And this is just 9.8. How far has it fallen in that is just calculated, and here's the numbers for it. But that is calculated by this formula. D equals VIT plus 1/2 AT squared, but this term is gone. That's a 0. And 1/2 A is just 44.9. So we end up with a very trivial, if you drop an object near the surface of the Earth, how far has it fallen? There is the trivial formula for it. Now, do you want to memorize these things? Probably not, because there's other formulas that we have to worry about as well. Like how fast is it going? We'll use this formula. VF squared equals VI squared plus 2AD. This is 0, and that's 9.8. So VF is going to equal the square root of 19.6 D. That's one way to calculate the velocity. If you have the distance, you can calculate. So every formula that we have, if you put VI to a special 0 and a to 9.8, you get simplified versions of the formula. We're not going to memorize them. If you do, so be it. If you drop an object, how fast will it be moving after 1 second, after 5 seconds? Okay, we're not calculating it here. We're just looking at the formula. The chart. After 1 second, it's going to be going, so the t of 1 second is 9.8 meters per second. Oh, sorry, the v of 1 second. The t of 1 second is 1. The v of 1 second is 9.8 meters down. And the velocity at 5 seconds is 49 meters per second down. You can write down there. I'm just being simplified right now. Okay, now let's change the topic, change the question slightly. Okay, you understand where I got those numbers from, right? Okay, there's 49 there, just the speeds change as we do it. Now, if you throw an object up at 49 meters per second, how long till it reaches the top of the flight? I chose 49 because it's in our table. Okay, it's in the table. So this is the velocity that you're throwing it up at. And it's going to lose 9.8 meters a second every second. So after 1 second, it's going to be here. After 2 seconds, it's going to be here. After 3 seconds, it's going to be there. After 4 seconds, it's going to be here. And after 5 seconds, it's going to stop. Because it took 5 seconds to get there. If we dropped it, it'll take 5 seconds to stop. So the answer here is, how long will it take to reach the top of the flight? The time will be 5 seconds. Okay, that's just the chart. How do we calculate this? How do I do this in physics formula land? Well, this is the same as initial speed is 49 up, acceleration is 9.8 down, and the final speed is 0. Because when it's the top of the flight, there's the trick. As I stated standing up at the front of the class about 15 minutes ago. The top of the flight, the top of the motion, when it stops, is an important part of the traveling. Yeah, that's when it stops. So calculating the time, we have VF equals VI plus AT, and VF is 0. We get 49 up, which is negative 49, plus 9.8 down T. So you bring the 49 over here, you get 49 equals 9.8 T, and you get 49 over 9.8 is equal to T, which is equal to 5. So we can do it the old-fashioned way, and we will be doing it the old-fashioned way. Okay, and did you notice, as I said, I'm going to make my acceleration always positive. Okay, and then how much longer does it take to fall back down? If you throw an object up at 49, it takes 5 seconds to stop. It'll take 5 seconds to come back down. What goes up must come down. What speed does it land at? Well, it lands at 49. Sorry. It lands at 49 meters per second, and if it's a velocity, it's down, if it asks for the velocity. Okay, because the time up is the time down. Now, we could go through all the calculations that I did yesterday. We can do them all again to find out this. Okay? We could do it that if the displacement is 0 and the initial speed is 49 up and the acceleration is 9.8 down, we want to calculate the time, we would just put it into the formula of d equals VIT plus 1/2 AT squared, okay? And when we solve this, we get 2 answers when we plug these numbers into it. Because it's a quadratic, we get an answer of No, will we get two answers? Maybe. Anyways, that's how you would solve it. Okay, and you'd get a time of 10 seconds and 0. How high did it go? Now, I'm going to start using some fun logic here. If it goes up, it stops and then comes back down. How high it went is the same for both parts of the flight. This distance up is the same as this distance down. So you could choose to calculate either one of them. And sorry, for me, the easiest is always when VI equals 0, because all our formulas make it easier. If we take a look at all our formulas, right, we have VF is equal to AT, the VI disappears. We have D equals 1 half AT squared, right? And then the other one is VF squared equals 2AD. And the last one is D equals VF over 2 times time. These are the four formulas if VI equals 0. They're a lot easier to work with. And so this is my favorite version right there. How far does it fall after 5 seconds? Because we know it takes 5 seconds to come back down. So D equals 1 half AT squared. D equals 1 half 9.8 times 5 squared. This is going to be 4.9 times 25, and that equals 122.5 meters. Just showing how we could do it. And this is only taking the second part of the flight. Oh, by the way, if you had this chart in front of you, you could have figured it out right there. Something that falls for 5 seconds travels 122.5. Okay? Now, I love analyzing this data. You might not understand why, but I just love it. After 1 second, it fell 4.9 meters. After 2 seconds, it fell 19.6. After 3 seconds, it falls 44.1. Pardon me. How much did it fall each second, though? So I subtracted these two. 49 subtract 0 is 49. 19.6 subtract 4.9 is 14.7. 44.1 subtract 19, because it had fallen 19.6 after 2 seconds and 44.1 after 3 seconds. So between the second and third second, you have to subtract them. It falls a total distance of 24.5. So this is how much distance it travels each second. And if I add up 4.9, 14.7, 24.5, 34.3, and 44.1, I get 122.5. So I'm actually seeing the distance that it travels each second. And notice, the distance that it travels each second is increasing. Why is it increasing? Because you're traveling faster. If you travel faster, you travel more distance each second. Okay? And this part that I'm talking about now, I'm really playing with the data and I'm really sending it to the math people, especially the people that like calculus. Okay, there's a little bit of calculus involved here, but watch this. This might blow your mind, but it might not. Probably not. What's the difference between these? That's 9.8. What's the difference between these? 9.8. What's the difference between these? 9.8. The difference between these? 9.8. Oh, this is fabulous. right? This is fabulous. You may not see what's going on, but oh, what's the average of the speeds between the fourth and fifth second? You start at 39.2 and you go to 49. What's the average of the speed? 44.1. What's the average of the speeds between, let's say, second and third second? Your second at 2 seconds, you're 19.6. At 3 seconds, you're 29.4. The average speed there, if you average those two numbers out, is 24.5. So these are the average speeds. And then when you average these two numbers out, say let's the change between 2 to 3 and 3 to 4 is 24.5 and 34.3. When you average those average velocities, when you average the average velocities, you get the acceleration. Oh, it's fabulous. It's fabulous. You'll like it when you get to calculus, and this is beautiful. Okay. Last but not least, let's take a look at if you throw an object up and catch it 8 seconds later, how high did it go, and what speed did you throw it at? Okay. So it goes up, stops, and comes back down. So you could do it the old-fashioned way that 2 days ago you would have done. You would have gone displacement equals 0, time equals 8, and the acceleration is 9.8 down. And then you'd go, that's for the full flight. Then you calculate this, you'd calculate the initial speed and the final speed through this, and then you would calculate how high it went. We don't have to do this now because it takes 4 seconds to go up and 4 seconds to go down because it's 8 seconds up. So what you write down there, you go 4 seconds up, 4 seconds down, okay? And then how high did it go? Well, you use this and you go d equals 1/2 at squared. The distance is 4.9. Well, actually, I don't want to skip that step today. 1/2 9.84 squared, and we get 78.4. That's how far it fell, which is how far it went up. And what speed did you go at? Well, the VF is equal to AT, which is 9.8 times 4. So it was 39.2 meters per second. We're still doing the physics, but we made it a much simpler question by only looking at the second part of it. Are you allowed to do that? Yes. I call it a Mr. Curlism. I teach you this skipping step, this understanding of physics, and then go ahead and use it. What goes up must come down. The time up equals the time down. And how high it went up is how far it fell down. And the speed that you threw it up is the speed that you came down at. Okay? If you throw an object up at 29.4, what speed will it have after 5 seconds? Do not assume it's going to be at the same height. That would be a bad one. Because if you take a look further, it says, what is this displacement at this time? And then if you didn't have the table, how would you calculate it? So if you threw an object up at 29.4, what speed will it have after 5 seconds, and what is its displacement? Let's just take a look at the table. 29.4. Okay, so I'm just going to erase all my highlightings there so we can see what we're doing here. Okay, so it starts here. So after 1 second, it's going to have this speed up. After 2 seconds, it's going to have that speed. At 3 seconds, it's going to be stopped. After 4 seconds, it's going to be back to here. And after 5 seconds, it's there because it goes up here and then starts falling here. So after 5 seconds, it'll have a speed of 19.6 down. How far will it be? What is its displacement? Well, it'll go up 44.1 meters and it'll come down 19.6. So it'll have a displacement of 24.5. Okay? I don't want you to use this table, but that you can see how good that table could be. If you didn't have the table, how would you calculate it? So this is how you'd calculate it. VI is equal to 29.4 up, and what will its speed time is equal to 5 seconds, and the acceleration is 9.8 down. So again, Mr. Curl always makes up negative, down positive, it doesn't matter, and we want to know its displacement. Displacement is equal to VIT plus 1/2 AT squared without the VF, and this is easy. 49, watch this is going to be good. Negative 29.4 times 5 plus 1/2 9.8, and that's going to be positive 5 squared. So 5 times 29.4, 5 times 29.4, 147, and that will be negative plus, and this is 122.5, so I have to subtract these, negative 122.5. Okay, let's back it up, that didn't work. 147 subtract 122.5 is equal to 24.5 meters. And this will be a negative because this is a larger number. So the displacement is 24.5 meters up. Okay, so I'd like you to give number 5 a shot right now. On planet Physics Alpha, Mr. Curl is standing at the edge of a very large cliff. Mr. Curl fires a loaf of bread upwards at a speed of 24 meters per second. And at a point 45 meters above Mr. Curl, a very large flying alien catches the loaf. Determine the time the loaf was in the air. And I want to use the gravitational field strength of 4.8. Because this is on another planet, so it's not 9.8. Okay, now here's my hints. Show all work and be careful of your signs. Mr. Curl makes down as positive, so if you want to see my answer compared to yours, okay? And hint, it goes up, passes the alien on the way up, and then comes back down and passes the alien again. So there are actually 2 times, therefore 2 speeds. Okay, just picture it. Here's Mr. Curl standing on the cliff, and he tosses the loaf up, it stops, and then it comes back down. This is the way it would go. But if there's an alien here standing on his aircraft and he's catching it, that's not weird alien here. He's going to have lots of arms. There's weird alien, and he catches it here. It passes on the way up, and it passes back on the way down. So there are two answers that he could be. He could catch it as it goes up, or catches it as it goes down. So give it a shot. Okay, go ahead. It says step one, write the final velocities, plus or minus for the two answers. So you will use VF squared equals VI squared plus 2AD, but write down the givens, and then find the times. You'll use time is equal to um, probably VF minus VI all over A. And you'll use the positive and negative values of VF there. Okay, give it a shot. And I'll put the answers down in the caption in the comments below. So enjoy that, please. And subscribe, comment, leave lots of comments, and smash that like button 5,000 times. Thank you.